Professor Jay Werber here from the University of Toronto. Going to discuss problem set 5, the Haber-Bosch process from CHE 208. And so we're considering the Haber process below to produce ammonia from nitrogen and hydrogen. The system is a reactor condenser, so the feed goes into stream 1 here, blends with the recycle. So this is the recycle, goes to the reactor. In the reactor, we have N2 plus 3H2 goes to NH3. But we're saying that this is in equilibrium in this process, right? And then the reaction products goes out in stream 3, goes to the condenser. The condenser is a total condenser for the ammonia. This is actually a bit of a misnomer. So the ammonia, all of it comes out this way, and then the residual gases are recycled. So ammonia goes out in stream 4, and then we have an overall conversion of 95%. So overall conversion of 95%. And the recycle ratio, so what we're going to call RR. This is the recycle ratio. And RR here is defined as the moles in the recycle divided by the moles, the fresh moles. In other words, this is N.7 over N.1. And so this is something that we're leaving as unknown. And we use a basis of 100 moles per second of fresh feed. So that means that N1 is 100 moles per second. All right. So that is the process in a nutshell. And so the first thing that the question asks us to do is write the equation for the equilibrium constant for the reaction and discuss if one should increase or decrease the total pressure in the reactor to increase the equilibrium conversion. So let's do this. So this is A. So the equilibrium coefficient here is going to be the partial pressure of NH3 divided by the partial pressure of N2 times the partial pressure of H2 cubed, right? And so this means that it's Y NH3 times the total pressure Yn2 times the total pressure, and then YH3 total pressure cubed. Or let me try and get a different color. Maybe that'll make it go faster. It does. I don't know why blue is so slow. So if we're going to break out the pressure, we have, oh, I'm very silly. So I did not balance this guy. So 2, oops, squared, squared, squared. So this is going to equal, so we have p squared up here, and so we have p squared over p to the 4th. So this equals y nh3 over y n2 y h2 cubed times 1 over p squared. So that is our equilibrium coefficient. And if we want to increase the conversion, right? So what is the conversion going to be? We want to maximize the amount of ammonia that's produced. So let's move this around a little bit. So we have YNH3 squared is equal to KEQ YN2 YH2 cubed P squared, right? So this is the mole fraction of ammonia. And so if we take the square root on both sides, we have this guy all to the 1/2 power times pressure. In other words, it's pretty clear that so if total pressure increases, then the YNH3 increases and conversion increases. Okay. So that pretty much answers question 1. So we want to increase the pressure of our system to try and maximize the mole fraction of ammonia. Of course, when this happens, you can do the exact same thing and then look at the mole fraction of, let's say, nitrogen, and see that the increasing the pressure will cause the mole fraction of nitrogen to decrease. If we're thinking about conversion of nitrogen, for example. So that's all great. And that is why in B, we assume that the reactor can reach equilibrium at a pressure of 200 atmospheres. So 200 atmospheres is 200 times the 1 atmosphere of pressure, which is fairly high pressure. And we have an equilibrium constant of 1.06 times 10 to the negative 6th. And now we need to try and solve this process. So let's go ahead and do it. Okay, so B, we have pressure is 200 atmospheres. KEQ is equal to 1.06 times 10 to the negative 6th. All right. Great. Okay, and this is, again, like sort of with a P ref is equal to 1 atmosphere for this KEQ. So that is our process. And what should we do first? So maybe we should redraw the whole thing and just have our things labeled. So this is our reactor. This is our condenser. We have our recycle. We have our purge stream. And we have our ammonia stream. So we have, let's label this 1, 2, 3, 4, 5. We have a splitter here. What do we say? The recycle stream was stream 7. And the purge is stream 6. Okay. So what do we know? So we have ammonia and hydrogen at stoichiometric ratio. Okay. So what does that mean? So we have so N1 is equal to 100 moles per second. And then we have N2, so let's see that. YI, this inerts, is equal to 0.04 moles of I per mole. And the residual amount is nitrogen and hydrogen, correct? And so in the feed, we have stoichiometric ratio of nitrogen and hydrogen. And what that means is that YH2 is equal to 3YN2, right? So that they are equal. And so it also, we have that YH2 plus YN2 equals 1 minus 0.04 equals 0.96. Let me go ahead and get my calculator. I think I'm going to be needing it. All right. So let's divide this by, so this means that, so we can plug this in, and we have, let's see, 4YN2, correct? So if we divide 0.96 by 4, that means that Yn2 is equal to 0.24, and H2 equals 3 times of that, which is equal to, what is that, 0.72? So moles of N2 per mole and moles of H2 per mole. Okay, so that's all great. Because we have a basis that is 100 moles per second though, we can just have that N1I is equal to 4 moles of I per second, N1H2 is equal to 72 moles per second. Sorry, I'm going to add a little space here. What happened here? And N1, N2 is equal to 24 moles of N2 per second. All right, great. So we have, let's see, stream 2, we don't really know anything about, right? But stream 1 is fully defined. So let's label stream 2. So what are we going to have here? N2I, N2 H2, N2 N2. The one thing we want to ask ourselves though is if H2 and N2 are at stoichiometric ratio in the feed, and then they travel together everywhere, are they independent? So let's ask this question. So are N2 and H2 independent? And the answer here is no, right? So for every single stream, so N of H2 is going to equal 3N of N2 in every stream. So we don't really need to define that. So let's go ahead and maybe only care about maybe the nitrogen. How about that? So let's go ahead and delete this. And are there any other species? We should only really have inerts, hydrogen, and ammonia, and nitrogen there. Great. And so then coming out stream 3, we have N3I, N3, N2, 3, N3, N2, and then the amount of ammonia coming out. Great. Here we have the ammonia coming out in stream 4. And then we have stream 5. Coming out. So let's just... So stream 5, we have N... How should we do this? I guess we don't really know the composition at all. So we do know that the compositions of streams 5, 6, and 7 are going to be the same. But for now, I'll just have it labeled as the molar flows. And we have the same thing in stream 6. And in stream 7. And the other thing we know about stream 7 is that the total number, oops, that was supposed to be 7s. We know that stream 7 is equal to RR times stream 1, or 100 RR moles per second. Okay, but we don't know what RR is. This is a variable that is still sort of undefined. All right, so we can do our degrees of freedom analysis now, sort of see what we can figure out. All right, so what should we do? So we know everything about stream 1, so we probably want to consider stream 1 in our situation. So let's do our degrees of freedom analysis. So if we do stream 1, what can we sort of have that be part of? Probably the place to start most likely is overall. That would make sense, huh? So let's do our overall CV. And so what number, so number of unknowns. We have, I believe, 4, right? So we have, 1, 2, 3, oh, no, just 3. Right? So 3 unknowns there. Is that correct? I think so. So we have 3 unknowns. And this is the amount of ammonia, the amount of nitrogen, and the amount of inerts. Okay. We have one reaction. And this is going to give us our extent of reaction. And then what do we have here? So we have, let's see. So there's 2 components. In the reaction that are independent. So 2 independent components. And so this is the number of independent unknowns. So we have two independent components, and these are, ammonia and nitrogen. Okay, so this is minus 2. And then we have one inert species. So minus 1, this is just what we call I. Let's see, we have our overall conversion is specified as 0.95, correct? So we have the overall conversion is 0.95, and then we have equilibrium in the system as well. So we have extra equations. And what I'm going to say is that there's only one here. So this is the overall conversion. And the reason for that is because in the actual reactor, it's reaching equilibrium, but the equilibrium is only applying to stream 3, and is not applying to the overall system. So because the recycle goes back, the equilibrium sort of doesn't quite apply for the overall CV. So we're only going to have the overall conversion here. And so we have 3 plus 1 minus 2 minus 1 minus 1. So we have 0 as our degrees of freedom. Okay. So let's go ahead and so this means that we're going to basically be able to solve for N4 NH3, N6 N2, and N6I, and the extended reaction. So that's all great. Okay, so where should we go next? So now we know N6, stream 6 is now solved for, right? So how should we do this? Maybe I'll underline them with green. Or maybe here. I will highlight them with rose. Okay. I would have just called that pink. No, I don't like that at all. Okay, let's use a different color. I will just... So these are now solved. Okay, great. All right, where do we go next? So looking at this, yeah, so this is where it gets kind of tricky. So the way that I solved this in the class before is just leaving RR as a variable, and then solving for RR at the very end, and having everything be as a function of RR sort of in the middle. So why don't we do that? Let's do a trick. So this is our trick. So I will do this in purple. So trick. Let RR be a variable that we sort of assume is known to some extent. In other words, we set the other values to be a function of RR. Okay, and so if we assume RR is known, so if RR is known, then we know N7, we know N6, and so therefore we'll know N5, which is all good. So let's look at the CV, the splitter CV. So this is streams, stream 5, stream 6, and stream 7. So the number of unknowns, the number of independent unknowns, because it's a splitter, it's all the same composition, is just 1. And this is just n dot 5, right? So n dot 5, so n dot 6 is known, and n dot 7 is equal to 100 RR, right? So we sort of assume we know that already. So we have the number of independent unknowns. Number of independent components is just 1. So we have 0 degrees of freedom. So now we know streams 5 is known, and all of the components in stream 5 are known as well. But they're as a function of the reflex ratio, or the recycle ratio. So weird thing there. We can do the same thing for combining streams 7 and stream 1. So at this point, we only have, let's see, we have 2 unknowns. Which are the inert and, okay, so what do we have now? We've solved all this. We've solved all this. And so now we're looking at stream 2, right? And so we have 2 unknowns. So this is the mixer CV, and this is streams 1, stream 2, and stream 7. So we have the number of independent unknowns. And this is just 2, and this is N2I and N2, N2. And how many independent components do we have? I think it's just 2 again, right? So it's just, here we have I and N2. So this is 0. So now we have streams 2 is known. And again, though, this is as a function of the recycle ratio. So we're doing very much a workaround here. But these are all solved for now. And so now the only thing that's remaining is stream 3, which is going to be the equilibrium sort of function. And so we have 4 unknowns here, right? So 1, 2, 3, 4. Oh, no, we have 3 unknowns. So 3 unknowns. But now we should be able to solve for the recycle ratio as well. So let's do the reactor CV. So the number of independent unknowns is 4, right? So now we're going to finally try and solve for the recycle ratio. We're going to try and solve for N3 I. Correct? Yeah. N3 NH3 and N3 N2. Okay. Great. And so that is that. We have how many reactive species? So the number of independent reactive species is just 2, right? So this is N2 and NH3. The number of inert species is just 1. And we would be totally out of luck, except for we have 1, which is that we are at equilibrium. And so this is 0. And so now we should be able to solve for everything. So that is the solution path that I'm working out for you guys. I do wonder if there might be a better way. But this is what we're going to do. So this suggests that the overall CV, what we could do is solve for streams 4 and stream 6. Just manually. That should be something we can do right off the bat and get the extent of reaction as well. But then after that, we're going to need to solve everything in terms of RR. And then at the very end, we will sort of bring it all together. So why don't we do the manual part first? And then we can do the rest in Excel. Okay? So yeah. Okay. So let's do our balances. So the easiest one obviously is the inert balance. So let's do the overall CV. So if we do the inert balance, we have stream 1 is coming in. Stream 6 is coming out. And this is just equal to 4 moles of I per second. Okay, so nothing crazy there. Let's use maybe our conversion. So we have 95% overall conversion. So this means that, what does this mean? So 0.95 is equal to, and this is again for our limiting reagent, which in this case is nitrogen or hydrogen, but we're using nitrogen as the reactant that we're measuring. So this is what's going in minus what's going out divided by what's going in. Okay, and so this is 24 moles per second of N2 minus N6 N2 divided by 24 moles per second N2. All right, so let's do this little math. So 24 times 0.95, so we have 22.8 equals 24 minus N6 N2. And so this means that N6 N2 is equal to 1.2 moles of nitrogen per second. Great. So that is our second thing. Our extent of reaction. So we have, let's do our nitrogen balance again, let's say. So again, for extent of reaction, we have that for species I, it's going to be what's coming in plus the stoichiometric ratio times the extent of reaction, right? And so for nitrogen, this means that N6, N2 is equal to N1, N2 minus 2 times the extent of reaction. Is that true? No, I think I'm wrong, right? So the reaction, our stoichiometry is that we have one nitrogen. So sorry, the stoichiometric coefficient is just 1. So minus 1. Great. So let's plug in our values. So we have 1.2 is equal to 24 minus extent of reaction. And sorry, I shouldn't skip units because that makes things confusing. So 1.2 moles per second equals 24 moles of nitrogen per second minus 1 mole of nitrogen per second times the extent of reaction. And so this gives us that the extent of reaction is 22.8. So that is fabulous. So now we've solved for the inerts, we've solved for nitrogen, we solved for the extent of reaction. So the only other thing is ammonia. And so in this case, we can use that same extent of reaction formula. So N4NH3 is equal to 0 plus 2 times the extent of reaction. And so this is 22.8 times 2, 45.6 moles of ammonia per second. All right. So that is solving for streams 4 and stream 6. And the rest we'll do in Excel. And I'm going to make that a second video and stop this one now.